So welcome to today's Meow video seminar, which is with André Schidler from the Technical University of Vienna. And André, I think, will tell us about how to use SAT solvers to encode different types of problems into SAT and solve them efficiently. So please, without further ado, André.
Okay, great. So this is work with my advisor, Stefan Seider, and the main part I'll present goes back to his idea from a few years back. So as you already said, the structure of the talk is 1 hour that is a bit more superficial, and then a break, and then 1 hour where I hope the discussion part is the main part, but I wanna, so starting with some preliminaries and overview, given the crowd, it's probably a bit unnecessary, but still I will go with some basics. I will talk a bit about our work for structural decompositions and with parameters, how we can apply, or how we did apply SAT to machine learning. And then the main part is the scalability and how to use SAT-based local improvement, which is the idea of Stefan Seider, to scale SAT to larger instances. And then the second part is basically what was in the first part, just a bit more in depth and technical details, and whatever questions you have, I'll be happy to answer. So the main takeaways I hope you get from this is either you have not worked with SAT before, have not tried SAT encodings, then I hope your takeaway is I should look at this. This seems like a viable method. Let's try this for my problem. If you already worked a lot with SAT, then I hope your takeaway is, okay, if I have instances that I cannot solve exactly with SAT, maybe try this approach I will present. So yeah, the prelims, probably not necessary for the crowd I see, but just weird to talk for 2 hours about SAT without ever introducing the basic problem. So we're talking about propositional logic formulas, where the smallest formula is just a variable that can take the value true or false. We can build larger formulas by either negating a formula. The negation is true if the original formula is false. We can join two formulas either by conjunction or disjunction, and for the conjunction, the resulting formula is true if both parts are true, and for disjunction, the resulting formula is true if either or both of the smaller formulas are true. Then Boolean satisfiability is just the problem of, given such a formula, is there a variable assignment such that f evaluates to true? And this is the prototypical NP-complete problem that has been widely studied, which is very nice for us because there's a lot of research, both theoretical and a lot of development for the solvers that can actually answer this problem. And it also allows us to encode a lot of problems in NP into SAT. And this is like a very trivial example of an encoding. It's just the question of, can we three-color a triangle, which is trivially true, as you can see in the figure. But it serves as a good example of how we can actually encode a different problem into SAT. So we want to color a graph in such a way that no adjacent nodes have the same color, and we have a variable for each node and color combination that is true exactly if the node has the respective color. And first we have to make sure that every node has a color. So we have this disjunction that says it has color 1, 2, or 3. We have to make sure that they have not more than one color. So we have to exclude the possibility that any two color combinations occur. So we have to say it has not color 1 and 2, the node has not color 1 and 3, and so on. And for each color, we also must ensure that for each edge, the color isn't given to both endpoints. So for the color J, we say 1 and 2 is an edge, so they must not have the same color, and the same for 1, 3 and 2, 3. So this is a very trivial example of we can see that we can how we can actually encode different problems into SAT. And why should we do this? So this is a graphic created by Armin Bier and Marian Heuler. I found it on Armin's Twitter account. This is just the winners of the annual SAT competition, and they evaluated it against the current benchmark set, and you see like a steady improvement starting from 2002 here. And then every year there's like at least some improvement until like 2020 was again a big jump. And when you use SAT solvers to solve your problem, first of all, this is a technique that has been successfully applied in industry as well. So it's not just theoretical. And for example, in hardware verification, and you automatically benefit from all the improvements that are achieved in SAT solver development. And the whole thing is well standardized. So at the moment, it's easy to replace solvers once you have your encoding. The format is standardized, how you get your answers standardized. And solvers usually work very well with the standard configurations. And the nice thing for me, from what I was working on, is that it is easy to add constraints to SAT encoding. So if you have a dedicated algorithm for your problem, it may work better than your SAT encoding. But then if you want to have special properties in your solution, then it's usually hard to adapt a specialized algorithm to this. But for SAT encoding, it's just a few extra constraints, which is usually easier to encode. And we'll come back to this in the next topic. So what goes usually into creating an encoding? So first you need a characterization of your problem that can be encoded into propositional logic. Usually different characterizations lead to different performance. And so it's good to be aware and to try different characterizations. And once you have this, you actually have a solver for your problem. And if you have a new problem that you want to look into, then this is often a very quick way to get an algorithm to actually look at, for example, real-world graphs and how your new problem behaves for these real-world graphs without investing a lot of time in coming up with a dedicated algorithm. And these first encodings usually work decently. And then the next thing you need is symmetry breaking, as you want to reduce the search space. And symmetry breaking is a bit specific. So you see here 6 different solutions to the previous problem of 3-coloring a triangle. And they're in a way all equivalent. So the actual color doesn't really matter that much. You just want this constraint that edges have different colored endpoints to hold. And here, if you just say the top node has to be colored red, then you already cut the search space from, or the solution space from 6 to 2, and you will ease the work of the SAT solver. And usually this is necessary for your encoding to be competitive. Is you need to invest some time in finding ways to break symmetries and think about symmetries. And then, of course, there's pre- and in-processing, which is just a quicker method. Usually, if you have pre-processing, it's usually way quicker than actually giving the task to the solver. So we usually...
Sorry, when you're doing the symmetry breaking,
yeah,
would that also be like generic tools, or you would do that already during your modeling, that you somehow know specifically how to break the symmetries and you do it while encoding?
Yes, usually we do it statically when designing the encoding. So more or less you either think about, okay, what are the kind of the equivalences you have in your problem and what the encoding produces, or you just look at your solutions. The talk by Marijn Heuler like 2 weeks ago in the seminar like motivated me to look a bit more into his work, where he also has a lot of in-processing where you, from what you get during the run, you derive new constraints that will eliminate symmetries. But at the moment, it's just in the modeling phase for what we did.
Mm-hmm. Okay, thanks.
Okay, so SAT is a decision problem. What I will talk about are all optimization problems. So to get from the decision to the optimization problem, we have some value x that we want to optimize, and we have to encode the constraint that x has to be smaller or equal to some constant for minimization problems. And then we have to do this for each solver call. So for optimization problems, we usually have to call the solver more than once. And we either start to increase this k starting from some lower bound, and then once we hit satisfiable, we know it's the optimal solution, or we decrease k starting from some upper bound, and then we will get SAT until we hit unsatisfiable, and then we know the previous solution was optimal. The nice thing about starting from some upper bound is that you basically get an anytime algorithm. So as long as the SAT solver found any solution for any k, you always have a solution you can return, and you let your SAT solver run for as long as you want. And you will always get a solution, maybe not the optimal one if you don't let it run to the end, but some solution. And So there are other solver types that you may use, max-SAT solvers, pseudo-Boolean solvers, and SMT solvers. And they can all solve SAT and a little bit more. And they give you usually more sophisticated methods to go about optimizing and then getting the optimal value. And they also have a lot of other features, but in this context, we use them mainly to get a better reasoning for optimization. But since they all solve SAT, and then for us, it's just the optimization part, it's different. I will refer to them during the rest of this talk just as SAT solvers. Yeah. So again, when I say SAT solver, it's SAT, max-SAT, pseudo-Boolean solvers, and SMT solvers. Okay, so the first topic I want to talk about are width parameters. Width parameters are just a measure of some structural property of graphs. You see, as an example, tree width below, you have some graph, you decompose it into a tree, and the nodes are so-called bags and contain vertices of the original graph. Without talking too much about what the decomposition actually does, the width you measure is in this case is the size of the biggest bag -1. And what it gives you a measure of how tree-like your graph is. So if your tree width is low, then your graph is very much like a tree. If it's big, it's not much like a tree. And this is the background that usually algorithms run much faster on trees. And what this gives you is, if you have a small width, then you can use specialized algorithms for the specific measure that can solve your problem quickly. So usually these algorithms are exponential in the width, but polynomial in the size of the instance. So as long as the width is small, you still get a good runtime bound. And but computing the minimum width for these properties is usually intractable. On the other hand, checking if the width is smaller than some constant is for some structural decomposition is tractable, but computing the minimum width is usually intractable. And for computing the width and this witness that is usually a decomposition, this is where SAT comes into play. Yeah. So the one reason why to use SAT encodings for this purpose is they usually perform well for width parameters, and usually use some heuristic to get an upper bound, and then you have an anytime improvement for your heuristic solution. So usually, if you have SAT calls, they don't take equal length. It's like the closer you get to the optimal value, the longer the SAT calls take by a large amount usually. So you can get good improvements for heuristic solutions even by running your SAT encoding as an anytime algorithm. And then coming back to what I said previously, it's easy to add extra constraints. So we had a talk at my university in the PhD seminar last week where a colleague was working on constraint satisfaction problem solving using hypertree decompositions. And they were working on getting the decomposition part correct, because they don't only want decompositions that are very small. They also, in width, they also want special properties for the vertices in the bags. So, and this is often the case that you have some property that would be nice if your decompositions have, besides having small width. And this is where SAT is really strong, because you can easily add constraints. And we worked on this in a paper last year, actually on this constraint satisfaction problem. And we did this for tree width and for hypertree width. And we said, okay, so in constraint satisfaction, you have variables that can have more than 2 values. And so you have domain sizes. And we said, we fix a threshold and we say everything that's above this threshold is heavy. Everything that's below this threshold is light. So you have heavy and light variables depending on the domain the variable can take. And if you look at the tree decomposition, what we then said is we want to not only limit the width of the bags, but we want to minimize the load, that is the number of heavy nodes in the bag itself. And if you do this, you can get nice runtime bounds for the constraint satisfaction problem, and you can also extend this to hypertree decompositions, where instead of minimizing the load in the bags, you minimize load in the hyperedge covers.
And just to clarify, I mean, one reason for looking at these parameters is that if you have a graph with low width of some kind, then you can often use efficient algorithms on it later. But here we're looking at computing the width measure, are we?
Exactly. So in a way, when you use these parameters, you shift the complexity of the problem from actually solving the problem itself to finding a suitable decomposition. But because once you find one, then the problem becomes easy to solve in theory.
And can you say anything about, I guess it depends on the problem, but like we can do it for small width, but what is small? Like how many digits do we want? Like, you know, width is a 1-digit number, or we're doomed, or we can deal with widths up to like 100 or 1,000, or it depends a lot on the problem, or?
It depends on the problem. So for tree width, the graph size is more the problem. It's this point comes back later, but so the graph size is more a problem than the width actually for computing the decomposition.
Okay.
And the same is true for hypertree decompositions, because the width does not increase the size of the encoding that much, but it's usually cubic in the number of vertices in the input graph. But I will offer a solution for that problem in a little bit later.
Okay.
Right. So there have been a lot of problems, a lot of width parameter problems that have been solved using SAT. I will not go into detail for any of these. It's just there has been steady research for this topic since 2009, and we had a paper last year at Alnex, and the one I talked about before. So it's an interesting topic. Okay, so the next topic I want to talk about is applications of SAT in machine learning. And there, as far as I know, there are two main applications for this. The first one is you have some AI model and you want to gain insight about the model itself. So you have a neural network and you want to verify certain properties. For example, is it fair? Is it biased? And so on. Or you have a model that gives you some classification and you want to know why. So you want to find an explanation for this decision. And this is not what I would talk about. It's also a very interesting topic, but I want to talk about actually computing the models themselves using SAT. It has been work, among other models, for decision trees and Bayesian networks and decision lists and sets. And the nice thing about these three models is that they're easy to understand for humans. And the model, the motivation for looking at SAT for this, and this is a recent phenomenon. So for decision trees that started in 2018. So this has not been going on for that long. So the idea here is the topic of explainability for models has become bigger and bigger. So you don't want to only have a model that is very good, but you also want a model that you understand. And usually if you reduce the complexity, which for decision tree, for example, is the size of a model, it's easier to understand for a human. So traditionally for these models, you had some form of complexity reduction, but that was more to avoid overfitting, so that you wanted to generalize, you wanted your model to generalize better, and that usually means a smaller model. But actually, if it's more understandable for human, was merely a side effect. And now looking at optimal methods to really decrease the size of the model has been more interesting to a lot of people in recent times. And I will talk mainly about decision trees because this is what I worked on. Just an example to make sure everybody remembers what a decision tree is, and especially to fix some assumptions we make. So as an input, you have a classification instance. The rows are so-called samples, and the columns are so-called features. And in the last column is the class. And we assume that the features are binary, because that's easy to encode in SAT, and there are different methods how you can convert other domains into binary. And for the class, we actually don't care how many classes there are. There can be more than 2. And and the general task of a classification problem is you want some model that can correctly classify your samples, and you actually don't care that much about the input data, the training data, but you want it usually want it to perform well on data it has not seen yet, but you assume that that the training data is similar to the data you have not seen yet. So you try to train your model to correctly classify the data you put in. Then on the right side, we have a decision tree. This is just a binary tree. And on the internal nodes, you have features. And on the leaves, you have classes. And if you take the sample, for example, sample 1, you go to the root, you say, is it sunny? Yes or no? No, it's not sunny. You go to rain. Does it rain? It says yes. So we go left. Is it windy? Yes. So we go left. We go right. And then we say, no, we don't play golf. I don't know who, like this is some sample I found. I don't know who goes out golfing when it's rainy, but for some reason it's okay if it's rainy, not windy, to go play golf. But this is the way we go about finding the class. Yeah? So we just follow a path to the leaf. And the nice thing for decision trees is this actually gives us an explanation for the decision. Yeah. So now you know that the criteria for deciding to play golf or not is windy, rain, and sunny in this case. Another example for decision trees from the talk that Kevin Leighton Brown gave last week. This is more like a real world application. So you have a very simple decision tree with 3 leaves and 2 internal nodes. And that actually, I think it has a prediction accuracy of 70% if a random SAT instance is satisfiable or not. Which is, I think, a nice explanation of a real world decision tree that's actually quite simple and achieves quite good results. And so the decision tree learning problem we're trying to solve is the following. We want to find the decision tree that correctly classifies all the sample in the training set. And this is actually quite easy to do. Yeah, so this is what this illustration is. So if you start with all your data, and then you fix some feature, and then you put all the samples where the feature is true to the left, and all the samples where the feature is false to the right. And then you continue this until you have all these baskets with only one color. You have a decision tree, and you can do this in seconds for large instances. And this is what all the heuristics do. Basically, they have sophisticated methods for choosing these features, but they just always split the data in 2 until they remain with sets that contain only one class or some other termination criterion. So we need a second criterion to actually make it useful to use an optimal method like SAT. So usually you will try to either minimize the depth of the tree, or so the longest path between the root and the leaf, or the size of the tree. So either this is usually it means the number of nodes, but for decision trees often this refers to the number of leaves, which is kind of associated. And we focused on minimizing the depth for 2 reasons. First of all, it reduces the length of explanations. So if you want, which is usable for understanding the model. And also from a practical standpoint, for some reason, it's easier to encode into SAT to minimize the depth than actually the size. So by use decision trees at all, so it's an easy to understand model. If you give a reasonably old child a decision tree and invest 5 minutes, they will understand how it works. So if you give, they can then classify data. If you give an expert a complex neural network, they will not be able to tell you why it made certain decisions in terms of what of the input data was actually really important for the explanation, for the decision. So the following the path gives you an explanation, and then we focus on the depth because we want to bound the length of the explanation. And there are several encodings. As I said, this kind of started in 2018, which was not the first encoding for decision trees, but the first one that was able to solve small instances. Previous attempts failed for small instances already. Then there was an improvement 2 years later, which we use in our work, and then more work, and then our paper. And the important thing about this list is just that each encoding uses a different characterization of decision trees. So it's not somebody proposed an encoding and then we improve the encoding, but somebody showed that it's viable to compute decision trees using SAT. And then people came up with new ideas of how to encode this problem. So we are not yet at the stage where we just make existing encodings more efficient, we are still at the stage where we try to find new characterizations of the same problem. The problem is kind of that still that the encodings do not really scale to medium-sized classification instances. So you can solve small and medium small instances, but not medium or large instances. And usually classification instances in machine learning get quite large. And each paper that was in the previous list acknowledges this in some way, and they offer different solutions to actually scale this. So one is we reduce the number of features. You can do this in a way so that you can still distinguish samples with different classes. But what happens if you reduce the number of features is that you will then get duplicate samples, which you can remove. So you reduce the instance in 2 dimensions. But then you lose the optimality of depth or size. You may come up with a decision tree that's larger than necessary. You can you reduce more features, and then you lose the distinction between different classes, but you can limit this loss of information, and then we won't classify all the samples correctly, and you can just pick a subset of the samples and hope it's good. It's a good representation, and again, this won't classify all the samples correctly. But the experiments in the respective paper show this actually works reasonably well, because in machine learning you're not that interested in having a model good for the training data, but actually on the unseen data. So if you pick a good set of features or a good set of samples, you can get decent models this way.
One parameter or one direction that I didn't say is like you could say you can just decide that, for instance, my depth budget is 5. Do the best you can in this budget. Like, you know, minimize the classification error on the training data given the following depth. Would that make sense? Or did you think about it?
This is actually done in there's working constraint programming where they do this, as far as I know. For SAT, it's a bit difficult to express this training error. I mean, sure, you can just restrict the number of misclassified samples. Yes, and this is actually something that's on this list of things that we wanted to look at in the future. Because once you go from we want to have 100% training accuracy to we don't care that much about 100% training accuracy, the number of things you can do is kind of explodes in an interesting way. And so far we have not looked at this, but this, among other things, is like on the list of stuff to look at. So this is maybe the main part of what I want to talk about, is this idea of this framework that Stefan Seider proposed for scaling SAT-based solutions to larger instances, called SAT-based local improvement. And here, this is the problem I mentioned before, that SAT encoding, the size of the SAT encoding is often cubic or worse in the size of the instance, of the original instance. So while it performs well, at some point it just becomes too large to handle for your memory, for your hard disk. There are other constraints than just what the SAT server can actually solve. And for decision trees, some encodings are even exponential in size. And then the general idea behind SAT-based local improvement is just you start from a heuristic solution and then you try to improve it repeatedly. And this is actually not only interesting for heuristics, but a colleague of mine worked on this, and they looked at optimal anytime algorithms, where you say, okay, we swap this over after half an hour, and then we try to improve the solution with this method, and then compare it with running it for the same amount of time, just the anytime algorithm. And if you have like a time budget, you want to have a solution after 1 hour, then this solution actually performs reasonably well for this as well in many cases. So how does this look like? Coming back to the previous example. So we still have this sample, and the sample takes this path for the classification. And so every sample has like a path to the classification. And we say the sample is associated with each node it passes on the way to the classification. And now in parentheses, the number says how many samples are associated with this node. Yeah? So all the samples are associated with the root, and then it goes down with each split, and then until you're at leaves. And then the nice thing here is, so if you look at the decision tree rooted at this node, yeah, so you discard the whole rest. You say, okay, we look at just at rain, and you look at all the samples that are associated with this node. Yeah, so 6 samples. Then this is a decision tree that will correctly classify all these 6 samples. Yeah, so you can so a decision tree kind of consists of smaller decision trees for the subsets that are associated with the roots. And this is what we do with local improvement in this case. So we can pick any internal node, and this is a decision tree for the associated samples. And we can select small subtrees, and you see this here. We select this subtree. Then we look at only the subtree. We look at the associated nodes of the root. Then we try to come up with a better decision tree. And in our case, we want to limit the depth. For this instance, we come up with this decision tree that's more shallow. And then we reinsert this new decision tree instead of the old one here. And this, if you repeatedly apply this, this will decrease the overall depth of your decision tree. And this is the general framework of SAT-based local improvement is you repeatedly do the following. You extract a sub-solution within a given budget. Yeah, so you want your sub-solution to be small enough so that you can then handle the resulting instance in your SAT solver. You create a sub-instance from the sub-solution. You then compute a better sub-solution using a SAT solver. And if you find one, you just reinsert it before the previous one. So what you need are 2 things. So the first one is you need some property you want to optimize that's local. So def is local because you don't need any information from other parts of the decision tree to minimize the def. And then you need some method to extract the sub-solutions. And this has been applied for different problems. Tree width, branch width, tree depth are all width parameters. And then more recently, we looked at machine learning, Bayesian network, structural learning, and decision trees.
Do we expect to have any guarantees in the end? Like you run like your solver on the final instance to prove optimality, or you're just saying, well, at least it got better?
No, so actually, if you're not able, so if you are able to solve the decision tree instance, for example, optimally, then you don't need this whole thing. So the SAT encoding itself cannot give you the answer if it's optimal or not. And generally, if the solution is big enough, then you won't get any guarantees from this method. You will just get a smaller solution.
Okay.
So how does this work in practice? So these are the results from TreeBIF. They ran this on about 2,000 instances. You can see that about a third of them they could improve upon the best heuristic, which is decent given that heuristics for TreeBIF are actually quite good. And so they I think the lower limit for vertices in the graphs was 100 for these experiments. So these are usually quite out of reach for solving optimally with the SAT encoding already. So they didn't look at easy graphs. They took graphs that were hard to solve to begin with. For branch width, again, they were able to solve improve about half the instances. This table shows you some improvements of from the best instances. So you can see the graphs are decently large for this kind of problem. And yeah, you can get improvements of up to 10 in the width. And given that the runtime is exponential usually in the width, that decreasing it by 10 gives you quite better performance. For TreeDev, so these are all works I did not work on. This is what my office mate worked on. They didn't specify on how many instances they got an improvement and how many not, but on average they got a 46% improvement. But interestingly, what they did is they compared for some easy instances, giving the instance to a SAT solver to solve optimally versus using this SAT-based local improvement until the optimal result is achieved. And you see that this method comes to a way faster to the optimal value. And in this case, you can verify that it's actually optimal. Coming to the machine learning work. So in this experiment, again, my office mate tried the following, which I mentioned in the beginning. So he used an anytime algorithm and let it run. And after I think after 300 seconds, I'm not sure anymore, he stopped the solver, plugged the solution into the SAT-based local improvement, and then at various points in time compared how good the solution is using this method with the SAT-based local improvement compared to how well the solution is using this method. And you can see that the number of solved instances in this case solved means that it's I think it's a reasonable expectation that it's a good value that you achieved because you don't know the optimal value. You get a lot of results much faster. And actually, I think it's not 300 seconds. It should be about 30, probably off by a factor of 10. Yeah, but you can see that here you get a lot of results way quicker than if you just use the anytime algorithm. For decision trees, I can give you a few more detailed results because I actually worked on this. So here we compared against two state-of-the-art heuristics. The first one was C4.5, which is implemented in this toolkit that's called Veka. And you can see that the average depth of overall decision trees is 22, and we were able to almost halve it with our method. And the average accuracy on unseen data also increases, which is quite common for decision trees. If you make it smaller, it usually generalizes better. And out of the 37 instances we used, we were able to improve 36, where one instance was just so easy that the heuristic already solved it optimal. So for the second heuristic, ITI, interestingly, it produces more balanced trees because the number of nodes is very similar to the Veka trees, but the depth is lower. So here, of course, there's not that much to gain comparatively, but it's still a 20% decrease in depth. And the testing accuracy only increased slightly, although it didn't vary that much anymore. And again, an improvement on all but one instance, which was trivially sized. These are just some hand-picked instances. They're not necessarily the best instances, but of course good instances. But you can see here we have a large instance with 24,000 samples. And here you get a decrease of like depth 16. And so this is more to illustrate that it actually works on quite large instances as well. So this is the largest instance. And again, significant decrease. For these larger instances, they also have very large decision trees. It actually would probably produce better results if we let it run faster. So we gave it 12 hours to come up with the best improvement it has. For these large decision trees, there's still much potential that could be gained from running it longer. And here we have a medium-sized instance where you can see that here the decrease is much bigger, just because the algorithm can search more of the decision tree. And also the increase in accuracy on unseen data is quite significant. And for the other heuristic, so again, here the same instance, just to have a direct comparison, it's indeed much more shallow. But interestingly, the relative gain is about the same. It's just that absolutely it's much less. Here we have a medium to small instance, also works quite well on this. And here we can see that it's not guaranteed that the accuracy actually goes up. So in our experiment, it never went down more than 1 point something %, but it can go down if you have bad luck. Yeah, and then what do we want to work on in this regard? So first of all, if you look at this, the first thing that popped into my eyes, you should be able to parallelize this because you work on independent parts of the graph in an independent way. At the moment, the problem is it's implemented in Python. And multi-threading in Python is not really worth it because there is no real multi-threading in Python. Yeah, next thing is that there is work on caching for decision trees. So you often pick this, like in different parts of decision tree, you often repeat the same sub decision trees. So it pays off, or it may pay off to cache already existing computations to then look them up and not recompute them. There are other speedups. As I mentioned, it's at the moment implemented in Python. There's by now a lot of extra code that is not SAT codes where it would pay off to actually re-implement it in C++ or something faster. Then there is the big question of pruning in regards to decision trees. I will come back to this in the second part, but this is an open question. As Jakob asked before, then there is the question of, okay, if we relax the conditions, so you either work on an incomplete training set, so you remove some samples or features, or you say you allow for misclassifications. How can we get different results? Can we get better results? And this also ties into the last part. There are other optimization goals than depth and size. For example, a balance between misclassification and size. You're happy to add extra nodes if they correctly classify a lot of samples, but if it's just one more sample, you then don't add it. Okay, and I think this is about the time for the coffee break. A bit shy of 50 minutes, but reasonably close out.
I had a question. How important is the SAT solver you use, and which SAT solver did you use?
So the SAT solver we use is important. We use Glucose 3 because it just performed best for this.
So you showed the graph of the SAT competition, but actually use a SAT solver from 2010, right?
Yes, sure. I mean, this comes back in the second part as well. I mean, different SAT solvers are better for different problems, and you will only know which one is best for the problem at your hand if you try it. Okay. I mean, SAT solvers in the competition are they are good at solving the instances in the competition. That does not mean that they're good at your problem.
But you don't try to tune the SAT solvers with using one of the billions of options they have.
That would probably be a good option. So for the work we did so far, it was more important to check if the method is viable, and the next step would be to actually check if you can make it reasonably fast. This is I mean, I think the gain from tuning the SAT solver will probably not as big as the gain from actually parallelizing the whole thing.
Yeah, sure. Yeah.
So there are a lot of construction sites where you can get more benefits. Actually, for the SAT solver, it was interesting because Glucose has another advantage over other SAT solvers. It's just that for this problem, it consumes a lot less memory, which started to become an issue. For some reason, I don't know. It's not the general observation. It's just for this problem, it consumed less memory. And it has the nice feature that it actually tells you when it will run out of memory instead of just crashing.
Okay.
So these are two extra reasons why we use Glucose 3.
Okay, thank you.
But it's an interesting question, right? Because this has been discussed also in the, I think in the SAT community, when you look at these plots of performance improvements, like that if you, I think there have been claims that, well, if you would take that which solver comes out on top depends a lot on which year, which benchmark year you use for your competition benchmarks. And then there are some people who've been saying that no, that the difference isn't so great. I guess I haven't investigated it in detail myself, but it is interesting. I mean, the conventional wisdom, I think, has been that SAT solvers somehow auto-tune to give good overall performance. But the fact that you're using an old solver kind of suggests that, well, some of these new tricks that have been so successful in the last few years maybe are not so good for this problem. And then it might be interesting to, if you take a, like, I don't know, I suspect like a solver like KiSAT or something, which would maybe have support for switching on and off a lot of different options, to play around and see like, okay, what is it that is helpful here? Like, should we be, we should switch, you know, it's more, never do chronological backtracking, or do chronological backtracking, or keep more clauses, or keep less clauses, be more aggressive when you erase, or like, don't do this phase saving, or do this phase saving, or.
I know that Marijn had a similar observation at some point. So he had some XOR, I think it were XOR problems, where he also found that, actually, I think in this case was Minisat that performed better than all the winners of the SAT competition after. So
yeah, one of the difficulties of doing this, if you're solving optimization problems, is that the best set of options you use depends heavily on whether you're close to the optimal value or not. So if you tune it on a bunch of instances that are not close to the optimal value but tend to be relatively easy, you'll probably get a solver that performs very, very badly when it's close to the objective. So in some sense, you want you want to do the opposite of what a good solver does on sufficiently easy instances. So
you're saying we should not, like, the behavior of the solver, it should switch options on or off depending on how the solving process is going. Like, now I think I'm close, so now I switch to this behavior.
yeah, or you have a pre-solve configuration. So if you are a very long way away from the objective, you've probably got a relatively easy instance. So you design a pre-solver that's good at easy instances. You run it for a few seconds and then you switch to your good solver afterwards.
Another idea we had at some point was that if the runtime increases surprisingly fast, we assume we are close, and then we decrease the bound a little bit and see if we get answered. And like kind of guess from the behavior of the solver if you're close or not. But I also don't know, like, I don't, it's all in the competition set, there is like, I get like, I guess like 2 or 3 instances of each problem actually. So even if the solver doesn't perform well on your problem, there are not that many instances in the set that can still perform well on enough others. If your problem is even in the benchmark set.
Other questions, comments before we take a 10-minute break? But this is a very good time for questions. Yes?
Hi, I would like to ask maybe 1 question or 2 questions, I'm not sure. So I don't know much about this at all, but 1 question is, do these algorithms use randomness? Are they random?
So my part or the SAT solvers?
Both.
So as far as I know, yeah, there's randomness in SAT solvers.
So maybe I will tell you, so it's related to what maybe Jakob asked in the beginning. So one thing you could potentially do is run this until you get something. Just prune the decision tree at depth 10. So it's no longer perfect. And then you do it 100 times and then take majority of the 100 trees. This is called the random forest in the machine learning. So such a mechanism sort of perhaps can give you immediately better generalization.
Yes, very probably. The problem with random forest is then you lose the explainability, because a random forest is again not really easy to understand. Why? Because you usually have like a lot of partial decision trees that in conjunction form a classification that it's yeah. So I mean, I proposed this at some point to my advisor to look at random forests. Like the list, so the kind of the list of things we can do increases way faster than we can work it off.
And maybe it's related to the same problem of explainability. Somehow it seems that it's also related to previous talks to use a version of decision trees. You can have a linear threshold function at every gate. So we sort of compute some linear function of the input and check if it's more than some threshold or not. This sort of corresponds with these cut-in planes proof systems. Does it so?
You mean for the optimization goal, or?
So you can potentially find much trees of much smaller depth using this, so it's a different type of trees.
Yes, yes, and so what you usually do is that you kind of define a penalty for increasing the depth of the tree. So you say you kind of try to find a balance between increasing the depth and classifying more samples, and you say it has to be really worth it to add more nodes. And then you have like an objective function that balances the two of them. And there has been research in this for decision lists where they do this with MaxSat, where they directly encode this objective function into MaxSat. And then you can because it's kind of a waste if you add like 20 new nodes for a whole new layer of the decision tree to correctly classify one more sample.
But Amir, are you asking about like the test in the node in the decision tree? Because I guess in general decision trees, they can make any decision on the data. I mean the decision to go left or right in a node, I guess, is an arbitrary Boolean function, right? It's not necessarily a linear threshold function.
Yeah,
in this case, it's just variables as far as I know.
Yeah, so here the assumption is that you have binary values for the features. So it's just it's true or it's false.
Oh wait, am I confused now? You're querying just a feature. Sorry, I guess I'm totally bombed out. Sorry. Yes.
So in the node,
yes.
and I think in general, what heuristics do for general data is that you try to find a good threshold to say left or right. That gives you a good classification. So you don't get like this. You don't always get discrete values or like binary values. You usually get larger domains, and then you have to find the threshold of when to say left and when to say right. This is not what we do here, because we assume that we already have it binarized some way.
Okay, let me just, because I feel that was an immensely stupid comment on my part. So let me just go back to it again. So we're of course doing a we're doing a classic decision tree. It's just asking it about the value of a variable, whether it's true or false, and acting accordingly. And okay, so what you're suggesting is that we should, instead of just asking about a single variable, we should have some kind of linear function on a bunch of variables and branch on top based on that. But I guess, do the ML people use such? I mean, that's kind of getting closer to general activation functions somehow. I guess the search space would explode, no? I mean, the coefficient weights, how do you look for those?
So here we have an example. Here you have 3 features for the temperature. And what the input data looked like was just the temperature. And then somebody manually kind of defined, okay, 3 different regions, and then you have binary values that say, is it in the cool region or in the hot region or in the temp, in the mild region? And what general decision heuristics can do is they actually find the threshold to subdivide this. So you don't have to do it manually, or you don't have to do it in the pre-processing step for the data. But as far as I know, usually you just have a threshold, or you that separates this.
I think this is not the question of whether your domains are Boolean or not. This is, you could imagine, like you could imagine a decision node that just says, what's the sum for the rain plus the wind indicator? Okay, and if this sum is, you know, if I don't know, if this sum is greater than some value, then based on that sum, I go left or right. I think this is what Amir is proposing. So it's a more powerful, like it's not just looking at a single variable, it's summing up the Boolean values of a bunch of variables, possibly weighting them appropriately, and then taking a decision based on whether that weight is above or below a certain threshold.
Isn't that what a neural network does?
So every gate does this, but it's not structured as a tree. So here the nodes corresponds to sort of ends of variables or end of literals, right? If the gates are linear threshold functions, then every leaf is a polytope, like a convex polytope, an intersection of half spaces. Some region in space that is nice. So I'm not sure how does it go in terms of explainability, or how is it called?
Yeah, there are different terms, and that like 2 months ago, I think it was 2 months ago, I tried to look up the definition, and there is no definition for any of the terms. There are 10 papers that have slightly different definitions, but yeah, it's usually interpretability for models. I think it's the usual term.
So yes, I mean, you're proposing like a tree-like neural network model as opposed to DAG-like. Is that what you're?
Yeah, but so this sort of corresponds to the cutting planes proof system. So it's sort of somehow just resonates with previous talks.
I mean, it generally sounds interesting, but then you need some way of, like, in the end you need some way of gradient descent, because you need to kind of find the optimal weighting of the different features for each node. So it sounds very interesting, but I see no way to do this with SAT. This looks way too continuous to do with SAT. But it also sounds very much like a tree-shaped neural network in a way, because
I can imagine how one can use randomness to do a non-trivial discretization, but maybe it's not.
It would be interesting to.
Another comment regarding this idea of random forest, I think diversification of solutions would be an issue, in the sense that my understanding is still that modern SAT solvers should be thought of mostly as the deterministic algorithms. Like it's not like they if you run a SAT solver 10 times that it will give you wildly different results. It's like the most important heuristics are fully deterministic. And then of course, if things happen, like if you permute your input in some way, or if there are some weird, things happening in your initial phase when the SAT solver is starting and collecting data for its heuristics, and something happens and it's the instance is somehow unstable, so that the solver can veer off in different directions, then different things can happen. But like in general, the solver as such is very deterministic.
Yeah, so I don't know. I have no idea, but something that is done, I think, or at least theoretically done in machine learning is boosting. In this case, what does it mean? You build the first tree, you cut at a depth 10, then you make a lot of errors. Then the next iteration, you just work on the errors. And then you get another tree, and then you do majority and just focus on the errors again. So you get potentially better and better because you just focus your attention on what you're missing.
But then you would be weighting your first tree sort of higher than your, like every new tree gets comparatively smaller importance.
So there are, I think there are a few ways to implement boosting. So there are multiplicative weights and additive weights. So there are a few ways to implement it, but just perhaps it can give better generalization.
That's an interesting. So what do you say? Should we take a 10-minute break?
Yeah, sure.
So then let's take a 10-minute break starting now. So we're back after the break and we'll now hear Andre's second half of his seminar, please.
Okay, so first thing I want to go a bit into detail is, okay, what do you actually do, or what do you have to think about when actually implementing SAT-based local improvement? So the 4 things you always have is you have to have a problem, of course, but the problem has to be suited to be locally improved. So you have to have some optimization value that you can actually improve in a local manner. Yeah, so if you need information from all over the tree while you optimize the value locally, then this will not gonna work. You have to have some property that you can actually evaluate in a local way. So if you have, for decision trees, it's nice because you usually optimize the size or the depth, and this you can do for a subtree. And if you do it for a subtree, this will automatically decrease the size for the whole tree. So this is very local, it's very nice. And then you need some heuristic to actually compute the initial solution, yeah, because you start from a heuristic solution. And apart from you need a heuristic, it also pays off to look at different heuristics, because just because a heuristic is good, it doesn't mean it works well with local improvement. Maybe a bad heuristic works better because it gives the local improvement more chances to improve. So this is again something you usually only find out when you benchmark actually. You have a budget, so you want your sub-instances to be of a certain size. You don't want to spend forever in the SAT solver. You want to be within an expected time limit whenever you call the SAT solver. You need some way to actually extract the sub-solutions. And this also includes, often there are different ways of how you actually construct the sub-solution. So the different ways of how you actually construct the sub tree for decision trees. And finally, there usually a lot of options for local improvement to look at. You need some way to search through this, because especially for large decision trees, you usually won't get through all the options you have. You have to have some way of searching for it, such that you go for the biggest benefit first. So for the budget, is the first question you always struggle with is like, how do you actually determine the cost? This usually there's not a clear mapping between how big the encoding is or how big my subgraph is to how long the SAT solver will take, because I just recently ran some tests and you add one more sample to the whole to your instance, and suddenly it takes 500 seconds instead of 10. So there's no reasonable way to explain this. Just okay, something changed in the SAT solver and it takes longer. So this is not that trivial to find out. You have to decide how much do you actually want to invest. Do you go for short timeouts? Do you go for long timeouts? For decision trees, you usually go for longer timeouts. We have different configurations, but the longest takes a lot, about 15 minutes per SAT call. The colleague of mine who worked on Bayesian networks and especially on tree depth, for him it works best to just have like very few, very small timeouts of a few seconds. And then he can look at more options throughout the solution. For me, I have to look at large decision trees, otherwise there's usually not that much potential to improve, and then it just takes a certain amount of time to solve them. And then the next question is, you have to define a timeout because you don't want to let your SAT solver run forever. And then the question is, do you define a timeout close to what you expect, or do you give the SAT solver a bit more time to actually come up with a solution? And it also depends on how fuzzy your SAT solver times are. Yeah? So if you can pinpoint quite accurately how long the SAT solver will take, the timeout will probably be more close to what you expect. If it's very fuzzy, it's probably give it a bit more time. But it's always this trade-off between, do I invest a little bit more time such that I may get a solution, or do I already throw more time at something that I will get no benefit from anyways?
In one way of interpolating, I guess the way we usually write papers and are evaluated at competitions and so on is like you give a fixed time budget for everybody and then have a strict timeout. So I guess this sort of, at least for me, that tends to be how I do it, because that's somehow what I think is expected of me. But one approach, if you actually want to solve this in practice, you could measure like, how well is the solver doing? Well, it's really improving in every round, so I'll give it a few more minutes. Whereas, no, we seem to reach a plateau. Nothing have been happening the last 15 minutes. I'm sorry, you won't get more time now.
Yeah. So another way is to say, because we are now a heuristic, so we don't necessarily have to produce the best possible result. So another way is to say, okay, we have found already an improvement. We don't care that it's the best possible, but we already improved, so we don't give it more time. Or versus, we haven't had any improvement yet, so we give it a bit more time so that we get something out of this. So generally, what I mean, I will come to what we actually did in this regard, but. No, so we haven't looked at what you said. So the idea is that you look at the previous runs, or what? No,
somehow, I mean, you measure, like, suppose you have an anytime algorithm and you measure quality of solution over time. And as long as the derivative is looking great, keep going.
Sure, but
but when the slope of the curve like approaches zero, then nothing is happening, and then you decide, okay, seems like nothing more fun is happening today, so we'll call it quits.
Yeah, but it's hard to, like, if you have currently, like, you run your SAT solver on a sub instance, it's hard to estimate for a sub instance if this how it looks, right? And this is what I mean is. It's very, very hard because if you look at the instance itself, it has a certain distribution over the samples and the classes and so on. If you look at the sub-instance, the distribution can be way off because you already look at the samples that somehow made their way to this part of the decision tree, and then the distribution is different. And actually, so even if you, like, what we did is we actually tried the solver on different subsets of samples for different instances, measured this, and then tried to come up with like an estimate of, depending on the number of features, the number of samples, and the depth do you expect to then guess the runtime about. But this can change a lot if you take the same number of samples, features, and depth, and you just change the distribution within the samples a little bit. So for decision trees, it was really, really hard to estimate this. For with decompositions, as far as I know, this was way easier because you don't have samples that are distributed in a certain way. You just have a graph that is a certain size that you want to optimize for. Does this in any way satisfy your question?
I mean, we should let you continue also. Don't want to throw you off track right away, maybe later during the presentation.
Okay.
But we should give you a fair chance.
But if I get from this a good way to estimate this, then this was worth it. So the next thing is how do we actually select the subsolutions? And sometimes there are different ways to select subsolutions, even in the same area you identified with the strategy. And the next important thing is, since you create sub-instances, then you want to also usually look at pre-processing these sub-instances to get more bang for your buck in the SAT call. So you usually want to repeatedly apply pre-processing even for your sub-instances. And for the search strategy, so the question is where and in which order you look for your sub-instances. And the two things we usually look at is either we do it randomized, we just go all over the solution and try around. Especially when you have short timeouts, this is a good strategy usually. Or you start with the worst performing parts. So for the decision tree, if you want to optimize the depth, what we actually do is we look at the deepest branch and then try to optimize this, because if you manage this, then you will decrease the overall depth of the decision tree. And generally, if the branch is deeper, there are more possibilities to improve. Okay, so discussing these points with the example what we did for decision trees in terms of the budget. So the main driver of the encoding size, which is usually heuristically kind of decent measure for the runtime, the main driver is the number of samples and the depth or the size. And usually the number of features only linearly changes the encoding size. So we tried to find, so we ran the encodings for different instances and different subsets of the instances, and then we measured the time and the memory it took. And then we tried to come up with different configurations for, I think, 100, 300, and 800 second timeouts. And then we tried to set the threshold so that in most cases, the solver took shorter than the timeout. And then there are always outliers. And in terms of decision trees, this is very, very, very fuzzy. So it's very hard to predict from any of these metrics the runtime. And I also looked at the entropy within the set and other metrics, and just haven't found a good metric yet to that actually correlates well with the runtime. And then we came up with configurations, and these configurations say, okay, I expect the following depth. Or like my input instance, my subtree that I want to optimize for has the following depth. What do you expect are the maximum number of samples that I can have? So we create these configurations. And then, but even among similar sized instances, solver runtimes vary greatly. So it works, but I think if it's a good point to look here for improvements, because if you can pinpoint this more precisely, then you will decrease the number of solver runs that give you no improvement, which is a bit of a problem. Okay, how do we actually select sub-instances? We have two basic operations. We either select the whole subtree, this is what I was talking in the first part about, or general subgraphs. You see the difference here. So either I really select the full subtree, or I select a subgraph that is somewhere located in the middle of the tree. And then there are methods of how you can extract an instance from this such that you can reinsert the subtree into this spot. And using general subtrees just gives you more opportunities to improve. For example, especially, let's say you manage to improve something up here, this kind of trickles down to all the branches, and then you have again more chances to then decrease the size in some subpart of the decision tree. And then what we do is we often reduce the instance itself. This is kind of a pre-processing, and we use something that is called support sets. And the support set is simply a subset of features that allow you to clearly distinguish all the samples of different classes. And another way to define this is, let's say you take any two samples that have a different class, then in the support set has to be a feature that they disagree on. Otherwise, they're indistinguishable. And you don't want to have two samples that have different classes, but that you cannot distinguish anymore, because then you will have a misclassification. And what this does is you have a smaller set of features, which is already nice because it decreases your encoding size, and it also limits the possible assignments of features to nodes, which also makes the problem to solve easier. And then a lot of samples usually get the same values for the features, because now you have fewer values, then they collide, you have duplicates that you can remove, and again, you reduce the size of the instance. The disadvantage is that the optimal depth for the reduced instance is usually higher than for the unreduced instance. So you lose optimality, but we are already in the heuristic space. So as long as we can get some improvement out of this, we don't really care. And for the subtree selection, we don't really have a choice. We just select the root. But for general subgraphs, we try to find trees such as here that are really unbalanced. So you have like one branch that goes deep, and then other branches that go shallow, because there's an increased chance that we can actually rebalance the tree and decrease the depth this way. For the search strategy, I mentioned before, we choose one of the branches with the greatest depth. We try to select the biggest subtree that we can select without reducing anything. Again, we have a limit on the number of samples that we have to adhere to. So we try to select the biggest subtree without any reduction. Then if no change is possible this way, we try to select the biggest subtree with reduction, which is usually a larger subtree. And then again, if no change is possible, we go this branch up towards the root, and we try to search for general subgraphs along the way. So we try to reduce within the deepest branches first. And we do this for all the branches. And if there is no change possible, we terminate, which is not usually the case for larger instances that you actually terminate. Because if you at some point change something that may impact another branch, then you want to look at this branch again in the previous steps. So usually for larger instances, for decision trees, you don't get to the point where you actually want to terminate with the implementation we have. If you make it actually fast and you invest some time in making it faster, maybe yes, but at the moment, usually we run just into the time what we give the local improvement. Okay, so the thing I kind of alluded to in the first part is pruning, and this came up a bit in the discussion. So we actually, when we train machine learning models, we don't actually care about accuracy on the training set. So I said we try to correctly classify all the training samples, but nobody cares about the training set. All everybody cares about is how you perform for unseen data. So you usually have a test set of unseen data that you then evaluate your model on. And this is the important thing. If you have 0% accuracy on the training set, but you've somehow managed to have a good accuracy on the test set, everybody will be happy. And this is actually what decision tree heuristics do. So they compute a decision tree, and then they try to cut off parts of the decision tree that are not expected to generalize well. And there are different metrics for estimating this, but this is the only way you get a decision tree to actually perform well on unseen data, usually. Then, of course, these different pruning methods have their own parameters. Yeah, so the confidence interval, or like how much you punish more nodes, and so on. And like just looking at pruning for your, like, because this was asked quite frequently by reviewers, or when I talked about this paper, but how does it work with pruning? And then we said, yeah, we're going to look into this. And then we started looking into this, and then we found out, okay, these are like a lot of extra parameters you have to tune. So suddenly, like the amount of hyperparameters, like from the pruning method to the pruning parameters themselves, just went skyrocketed. We're still currently looking into this, and it looks very good. So it seems that if you apply local improvement to your decision tree, it actually also transfers to the pruned tree, so you get a smaller tree with the same or higher accuracy, which is very good. And the next thing is that what Jakob asked some in the first part is, okay, what if we allow for some misclassifications, then we have a lot of new options, which is kind of exciting, because then we can select larger sub-instances. We have more, because now we can just throw away some samples, and we have more chances for improvement. But the bad news for us is somehow, okay, now you have a lot more chances and a lot more hyperparameters that you can tune, because how large do you, how much samples do you throw away? How do you select the samples you throw away, and so on? These are all questions that currently pop up, and we are trying to solve. But generally, like from the first results we got so far, it actually looks very promising, and it seems that the local improvements actually transfer all the way down to the final decision tree if you apply pruning and then other methods. And we try to increase this benefit by looking at the partial data, in the sense that we don't look at all the samples and features of the training data. Okay, so this would be the jump to the next topic. So if there are any questions to the local improvement part, it's a good question to discuss this. Okay. So how do these encodings actually look like? So coming back to TrueWift, this is the example I had before, just a bit bigger. You have your graph, you have a tree decomposition, which is actually a tree, and the nodes are so-called bags. And this will be important, an important concept. And the bags are just subsets of the nodes of the input graph. I don't want to go into detail about how exactly, what are the conditions for a tree decomposition, because I will talk about a heuristic or a different characterization that implicitly will make valid tree decompositions. So if you're familiar with this, great. If you're not familiar with this, you don't need to know so far. And there's a characterization that's called elimination orderings, which is actually very, very suitable to encode in SAT. And all you need to get a tree decomposition is you have to order your vertices in some way. And for a heuristic, it doesn't really matter which way. There are ways, there are good heuristics for choosing the order. But the nice thing about this is, if you know this, you ever need a tree decomposition, like 5 minutes of coding and you have a tree decomposition. Of course, you can improve this, but still, like, it's a very, very neat way to, like, with a few lines of code, get a tree decomposition. So once you have this ordering, what you do is you create a directed acyclic graph, and you add all the graph edges as forward arcs. So you, I showed this here. You kind of draw a graph, and for convenience, it's ordered in the same way as the linear ordering says. Then you draw the edges again, but you let them point forward in the sense of the ordering. And now for each 2 outgoing arcs of a node, you also connect these the endpoints. Yeah? So if you look at C has an arc to E and to A. So we draw this fill-in edge from E to A. And then E has this fill-in arc to A, and it has this arc to B. So we draw another fill-in arc for A to B. So it's kind of, you have to compute the closure of this, and this is very easy to do for in SAT. So basically, the linear ordering is easy to encode because you just have variables that say A is smaller than B, and then you just and if the variable is false, then A is bigger than B. If it's true, it's A is smaller than B. And then all you have to care about is that this is transitively true. And encoding this rule is also easy in SAT. And then you can construct the tree decomposition the following way. So the bags are determined by the node and the outgoing arcs, and you connect the bags that share the smallest vertex. And this is shown here. So again, you have, for each node, you have a bag. So you have a bag C for here, you have a bag D for here. For C, you have exactly C and then outgoing arc to E, A, and B in the bag. And then you could connect this bag to D or to E, but because D only has A as the shared vertex, which is rather big, and the bag of E has E as a shared vertex, and E is smaller than A. You connect it to this bag. So this is a very neat way of quickly getting a tree decomposition. And if a SAT solver just has to go over kind of all the possible orderings to then find the optimal one. So what you then have to do is you want to limit the maximum number of outgoing arcs, because the number of outgoing arcs determine the width, and you want to usually get tree decompositions with small to optimal width. So you need to constrain them, and you can either do this with cardinality encodings directly in SAT or MaxSAT. We also looked at arithmetic constraints that SMT solvers provide, or linear constraints that are available in pseudo-Boolean solvers. So this can be generalized to hypergraphs. So hypergraphs are just graphs that have more than one vertex more than two vertices per edge. As you see here, this hyper edge is ABC. You can also have like normal edges with two vertices. And the generalized hypertree decomposition is a tree decomposition with one added thing. You have to cover the bags, and that means that you have to compute set covers for the bags. You see this is the two hyper edges AB and AH covering this bag. Here you have the hyper edge ABC covering the bag, and there is now one more vertex in the cover than in the bag, which is not a problem. The other way around would be a problem. And you have to do this for each bag. And the way this works is that you use a tree decomposition for the primal graph. So the primal graph is just the graph where you connect all the adjacent vertices. So you have like AD is an edge here that's normally here. Here you have a hyper edge A, B, and C. There where you connect AB, AC, and BC. So all these hyper edges become cliques in the primal graph. So okay, for this we already have an encoding for the tree width. Easy. Now we have to encode the set cover problem that we just add to the tree width encoding, and finally we just add cardinality constraints for the set covers instead of the arcs, because the number of hyper edges in the covers is actually what determines the width of the generalized hypertree decomposition, not anymore the size of the bags. Okay, and then what we actually worked on were hypertree decompositions. Don't want to go into too much detail, but the main difference is one extra condition. So we call these vertices that are in the cover but not in the bag omitted. And for hypertree decompositions, you say the tree is rooted. So this is actually the root. It is not placed here out of convenience, but it's actually the root. And now these omitted vertices are not allowed in the ancestors. So here we have C as an omitted vertex which occurs here. This is a violation. So this is not a valid hypertree decomposition. Here we have C as an omitted vertex, which does not occur here. So this would be okay, but this is a problem. And this is called the special condition. And the special condition is necessary because it makes the problem of checking if the hypertree width is smaller than some k tractable. So for generalized hypertree width, this is intractable. For hypertree width, this becomes tractable. And the reason why we were interested in is actually that this was the topic of the PACE competition 2 years ago. And actually, so it started with a colleague of mine saying, yeah, can you quickly implement this condition because we want to participate in the competition? And whenever somebody says, can you quickly, it's easy, you should know that this will not be easy and it will take a long time. And it turned out that this is tricky to encode this. It's not really straightforward. And also in terms of the SAT encoding, the problem seems harder because now you have to add extra constraints in already working SAT encoding. that and quite a lot of them actually. But interestingly, the benchmarks show that the hypertree-width encoding actually performs better than the encoding for generalized hypertree-width, excluding preprocessing, because the people that implemented the generalized hypertree-width encoding have like quite good preprocessing, which is an open question for us. But actually, but it was still surprising that the kind of harder encoding performed better. But it makes sense from a different perspective, because every hypertree decomposition is a generalized hypertree decomposition. And in a way, what we do is we add symmetry breaking to the previous encoding, because we just restrict the solution space for the SAT solver, which seems to work out in our favor. The disadvantage is that the hypertree-width can be larger than the generalized hypertree-width, so it's a bit of a trade-off, but still a nice result. And it's still an open question for us here is like which preprocessing actually transfers from the generalized case to the hypertree-width case. And these are the results. So this HD Leo, our implementation run on an SMT, SAT, and MAX-SAT solver. I'm very sorry that we don't have pseudo-Boolean results at this point for this. The red one is the reference implementation for this tractability paper. Yeah, so I said that with adding this extra condition, the problem becomes tractable, and this is the dynamic programming algorithm that shows this. And this is our first try. This is actually what we submitted for the competition, which was good enough for the competition. Then we forgot about it. The paper got accepted. Sometime later, it bugged me because I always thought this should be possible to do better and more efficient, and it turns out that this is possible. So this is this gap. And the takeaways from this graph for me are, first of all, we are better than the reference implementation, which is already nice. But also, it really pays off that you look at the characterization and you invest some time to get your characterization as best as possible, because this is like a jump from 1,100 instances solved to 1,800 instances solved. Okay, so any questions to this part? This is kind of getting to the conclusion.
I'm a little bit curious if you could tell me, when you say max, as presumably some kind of max SAT solver, do you know what went into that? And similarly, SMT seems to be a clear winner. What do you know what in the SMT solver is like buying you the extra power?
So for the max SAT solver, until the Simons Institute program, I was not that much aware of all the differences in max SAT solvers. Used UVR MaxSAT, which was at this point the winner in the MaxSAT challenge. The problem with MaxSAT is that for this type of problem, you have all these cardinality constraints for the different nodes, and then you have one kind of constant that you, and then you say you want, and then you have like one variable that says the cardinality for node A should be smaller or equal than 14, and one for B, and so on. And then you try to, for MaxSAT, you encode that that he should try to minimize the cardinality over all these different cardinality constraints. And this is, if you do it in the way UVR MaxSAT does, I think that it does not have any benefit over doing it in a linear search way you do it with SAT. I think it's just that the extra reasoning that the MaxSAT provides is just wasted here in the way that UVR MaxSAT does it. I think I'm really curious to try this on a implicit hitting set approach, because I think they probably will perform better than just the plain SAT encoding. Mm-hmm. So this is the MaxSAT. For SMT, I looked at SAT3 and Optima of SAT. At the time, for the first solution, Optima of SAT performed way better than SAT3. The last experiments I ran just before AAAI, they were about equal. And there we expressed this as arithmetic constraints, and it seems that I don't really know what about this makes it faster. It just seems that expressing this as arithmetic constraints.
So presumably like the linear arithmetic solver gets to work and does nice things and it helps somehow.
Exactly. But I only got to the somehow part, not the, okay, I understand why, it works better.
No, fair enough. I'm just curious.
Yeah. And actually, so for the few instances I tested this on, the pseudo, like the rounding SAT performs a bit worse. But since there is not that much time invested into the parameter tuning, I'm curious if rounding SAT actually how rounding SAT performs for this encoding. So this was the first one I tried it on. Okay, so the lessons learned for me from working with encodings is that the size of the encoding is actually not the most important thing, which is obvious for symmetry breaking because this is usually added. But we actually recently worked on another encoding and where we decreased the size, and it was a graph problem, so n is the size of the graph, the size from n to the fourth to cubic. And we were super happy that we were able to greatly decrease the size of the encoding. And for the largest instance, we're able to solve this means that we decreased the number of clauses from 30 million to 2.5 million, and the number of variables from 2.5 million to 0.3 million. We were not that happy when we found out that the larger encoding actually solved the instance within 2 hours, and the smaller did not solve it within the day. And so, I mean, the point that the encoding size is not the most important thing is not news to anybody who worked with SAT. But for me, this big gap in the size between 30 million and 2.5 million was still surprising that the performance difference was this big. And this is the same characterization. It's just a trick that we implemented to get from order 4 to order 3. The other thing is SAT solvers are great black boxes and oracles. They have the standardized way you encode your instance in. You give it a SAT solver, they give you an answer. Great. In practice, it's nonetheless good that you have some idea how they work internally, because long clauses are usually not really a problem because of the two-watch literal scheme. So if you can somehow save clauses by putting in longer clauses, it's sometimes a good idea. Solvers are really, really good at propagation. So this is kind of why I think this hack up there like caused more trouble than it benefits. It's just with the larger solution, it's just a lot of propagation and with very, very little guessing. And the moment you apply this trick, you kind of make the propagation harder for the solver. And generally size up to a point where like memory and disk space and other things become an issue is generally not a problem for the SAT solver. Like SAT solvers can deal with very, very, very large instances. And so before you cut down the size with things that make it harder to solve, maybe check if it's really a problem. Yeah, what we discussed after the first part a bit is different solvers are good for different problems. And you can only find out which solvers work well for your problems by benchmarking it over a set, not just for one problem, for one instance you have, but like over several instances, because for every problem we looked at, different solvers were actually the best. And then like the takeaway also from the last part is it really, really pays off to invest time into your characterization, because a good characterization can make it a lot faster. And this kind of concludes the talk. I hope that the takeaway for you is SAT-based algorithms are widely applicable, and it's a viable thing to look at when you want to solve your new fancy problem. Then embedding SAT into heuristic algorithms, it's actually a viable idea. So it's not a nice theoretical trick, but it actually works well in practice. And that the SAT-based local improvement is a good framework for trying to apply to your problem. So I hope there are more questions at the end of this part.
First of all, thank you for the seminar, applauding on behalf of all of us listening and enjoying. But you did ask for us to try to provide some counter enjoyment for you in the form of questions. I think I already asked a fair number of questions, so maybe I should give the others a chance before. I do have like 1 or 2 questions left, but I'll give the others a chance first.
So I have a question. You mentioned that size is not an issue, but I guess this also depends, right? You can't tell unless you try 2 encodings with different size and then know which one is better, right?
Yes, but the point is more that you, if you can just reduce the size without anything else, then okay, reduce the size. But if you have to make concessions to decrease the size, then often the concessions way heavier than the size decrease. That's more the point.
I was curious how you were using the SAT solver with symmetry breaking. So could you just dump the complete symmetry breaking, or did you do on the fly, or did you add clauses on the fly?
So for this, we encode this at the start. So we look at the instance. We for the hypertree decomposition, or and also for tree decomposition, as far as I remember, is you can, like, some orderings make no difference. Like if you can swap. So for example, if you look here, then if the example here, then actually swapping C and D will not make a difference. And this is like one similarity that you can break, is that when you detect that this will make no difference, that you enforce lexicographical ordering, for example. These are the things we usually do.
Yeah, just no, I don't know. I've just heard from people who did some encodings that sometimes the fact that you add symmetry breaking adds actually too many clauses, and then that software doesn't like it. But...
Yes, that's true. For the symmetry breaking works great for generalized hypertree decomposition. For hypertree decomposition encoding, it makes it way slower.
Okay.
Did you get any reactions from the people using other heuristic methods for computing these decision trees? Like, do they like this, or they don't like it, or
so the machine learning
try to ignore you?
Yeah, so the machine learning community is very good at ignoring logic people. So I think there was one at Triply, there was one person asking questions that had a machine learning background, but otherwise I think they just never look at what we do. I mean, the area is large enough in its own. So actually, like, so currently we're working on this application of pruning, because this was like the main thing that everybody was like, yeah, but like you never use unpruned decision trees, and I kind of hope that, given that the results stay as promising as they look, I hope that this will make a bit of a dent, that we can actually do better than state-of-the-art heuristics in a real-world setting, as long as you have binary domains, which is maybe not the realest world setting, but hopefully close enough for this community.
Any other questions, comments?
But like, I mean, I guess you still do have scaling issues with this tree stuff, right? I mean, even if you do all the techniques you use, I would expect that you, like, if you have really lots of features and lots of data, it still doesn't scale, or does it? Yes,
but the largest instance from the experiments is actually the largest one I found at the UCI machine learning repository, which is kind of a standard source for this. So the instances that we use are actually quite large. The thing is, it's not as if the heuristics are super fast on these. So for the pruning, we did hyperparameter tuning, and for the largest instances, even with heuristics, you have to spend over a day to let the parameters tune.
Okay.
Yeah. So it's so at this point, it's even the heuristics takes quite some time. So I mean, if you have a very small instance and you say, yeah, you just have to let our solution run for 12 hours after your heuristic ran for 0.5 seconds, that's maybe not a good selling point. But if your heuristic runs for an hour to compute the decision tree, then for 15 hours to actually prune the decision tree, then maybe investing some extra time into reducing the size of the decision tree in between is more viable. And then, of course, there's still this issue that we have it implemented in Python, and there's like a lot of performance gain, I think, if we would re-implement it in something that actually allows parallelization.
Do you know what percentage you spent in the SAT solver?
That depends, because this feature reduction I mentioned becomes quite a lot of work that is done outside the solver for larger instances, and then it depends on how much it needs to do this to get reductions. So it's for the largest instances, actually, as long as it doesn't go into the reduction, most of the time is spent in the SAT solver. As soon as it needs reductions, then the majority is actually spent on the reductions, which again is a point for re-implementing it in something faster.
Okay, so thank you so much. I think this might be a good point to declare the seminar officially over. Well, thank you so much, André, for this wonderful presentation.